All right, so we got page 10 and 11 for the running test slash midterm review. This is all the probability stuff. I would say that for these questions, you're basically going to have one of everything on here. The starting ones are all about how many possibilities you can find for certain stuff. So this first one says how many license plates are possible. The format is 3 letters and 4 numbers, and letters O, L, and I are not used. This is basically a problem you've seen a lot with this license plate format. It's essentially saying you have 3 letters and then 4 numbers for the license plate. And basically, each time you're going to pick one of those things. So there'd be 23 possibilities for the first letter. It doesn't say anything about it not repeating or anything. So basically, you have 23 possibilities for the next letter and for the next letter. Then for the numbers, basically digits go from 0 to 9, so you have 10 possibilities for each one of these numbers. And because the counting principle says since you're only picking one thing out of each, you can just multiply them all together like that. So it's going to be a really big number, but that should be the case. I mean, you're talking about a 7-spot license plate. That's kind of a big possibility of numbers. It should be if you want license plates for a whole state or something like that. So in the context of the problem, getting a really big number makes sense as an answer. This one comes out, actually I think we've done this problem a few times. It comes out to 12, 1, 6, 7, and then 4 zeros. 1, 2, 3, 4. So that would be 121,670,000. A lot. Which is why a state that had those kind of license plates would never run out of license plates. Okay, number 53 says at a Longhorn Steakhouse, each steak comes with a choice of 2 side dishes. So you're choosing 2, and there are 10 total choices. So how many possible combinations? This one even gives it away because it says combination in the problem. I don't know if I'll do that for you on a test, but just an idea, something to look for. So combination is where you have choosing a small group out of a large group, and the order doesn't matter. The order doesn't matter because it makes no difference what side dish you get first. As long as you get the 2 you want, what really makes a difference? So order is not important here. The formula would be n factorial over r factorial and n minus r factorial. So we write in the numbers we need. We have 10 over 2, and this would end up being 8. So we get the 10 to cancel out the 8, which leaves us with a 10 and a 9 on the top, and on the bottom, 2 and 1. That's 90 over 2, 45 possibilities. So it means that if you're just randomly picking 2 out of 10 things, there'd be 45 different ways you could do it. All right, number 54 says the world's strongest man qualifier points are awarded for 1st through 6th. As soon as you see a ranking like this, it ought to tell you that it's a permutation because order would matter. It matters who you select for 1st place and who you select for 2nd, and so on. If there are 12 contestants, how many different possibilities are there for 1 through 6? So basically you got 1st, 2nd, 3rd, 4th, 5th, and 6th place. That's 6 people out of the 12 contestants. Permutation formula just looks like a simplified version of the other one. Like that. So we have 12 factorial over what turns out to be 6 factorial. And that really only cancels some of it. You're going to have 12, 11, 10, 9, 8, and 7 all not canceled on the top. So that's something that you'd have to work out, probably on a calculator, I would imagine. Let's make sure you type everything and type it correctly. When you do, you get 665,280 possible ways that could be arranged. That's a lot. Okay, so we move on from how many possibilities there are to the next one, which deals with general probability. The problem with these kinds of problems are they can give you all sorts of different things. You never really know what you have. I actually also told you guys on the review paper to change this from 8 sides to 10 in here, so that it makes it just like the other problem. So here's the thing. You're looking at this and it says you're back at Longhorn Steakhouse. Suppose you want to have a 16-ounce ribeye, mac and cheese, and a salad. Okay, so that's like one whole meal that you want. Suppose there are 10 steaks and 10 sides to choose from. Let's say you tell the server to surprise you and you let him order for you. What is the probability of him choosing the exact meal you were hoping for? Okay, you were hoping for one meal out of the total. So the probability is going to be your one out of however many total we can figure out to put down here. So we've already figured out that the way to deal with the side dishes is because you're choosing 2 out of 10. So from number 53, we can look back and say, well, choosing 2 out of 10, that's a combination. Turns out there's 45 possibilities for the side dishes on the menu. Okay? Then, you have to consider that you're choosing one steak, and there are 10 steaks available. So, with there being 10 steaks available, what we're saying is that for the number of steaks, there'll be 10 possibilities. So to figure out how many total possibilities there will be 45 side possibilities for any steak you choose, and there are 10 possible steaks, so basically you just have to multiply it together. So it turns out that there would be 450 possible menu choices, which would mean your menu selection, the meal you want, is 1 out of 450. So that one actually takes into account something you already did in number 53. Number 56 is something we've been doing a lot of lately. It says, what is the probability that a randomly selected point will fall inside the shaded area? Almost like you were playing darts or something like that. What will be the probability that a random point that you choose will happen to land right inside that shaded area? And we always say that it's generally the probability of the shaded area over the total area. So the shaded area is the triangle. If you look at it, it's got a base that is the side of this square here. So the base is 5. And the height of the triangle is the same as this. It's also 5. So if we do the triangle's area according to this formula down here, the area of the triangle is 1/2 of 5 times 5 times 5. So 25 cut in half, the area of the triangle is 12.5 units per centimeter squared. And the area of the square, which would be the total area, the area of the square is just take the side of the square and square it. It's 25. 5 squared, 25. So again, with probability being the area that's shaded over the total area would be 12.5 over 25. And that would reduce to 1/2. So in this case, it came out really easy. It worked out to 1/2. Doesn't always work that way, but in this case, it happens. Okay, so now we're getting into a little bit more complex probability where this one deals with multiple events happening all at once. So it says, suppose you have a big bag of Hershey minis, 8 are dark, 6 are crunch, 7 milk chocolate, and 4 are almond. What is the probability of randomly selecting an almond, putting it back, selecting the crunch, eating it, then selecting the dark, eating it, and then finally selecting another crunch? It wants to know what is the probability of all of that stuff happening in order exactly the way we just said it. Obviously, it's a very hard thing to do for it to just randomly occur that way. It would be kind of incredible that it would happen if you could, like, think about it in the sense of, like, okay, somebody's going to do 4 picks out of a bag. What is the likelihood that it would happen this way when doing all of these various things? It's a very odd, very rare situation. Alright, so basically we're going to figure out the probability of this by saying, okay, each thing is an event, and we're going to be able to multiply those individual events together. So there are 25 total chocolate bars of some sort. So it says, what's the probability of selecting an almond? That's our first thing. So for the almond, it was 4 out of 25. Okay, you put that almond back in the bag, so there's still 25 in there. Now, what's the probability of selecting a crunch? Well, that one, selecting the crunch would be 6 crunches out of 25 total. Notice that that is like exactly the same as it would be if you didn't even do the almond part. It would still be selecting the crunch 6 out of 25. But okay, so after you get that crunch, you eat the crunch, and then it says, what's the probability of selecting dark? Well, okay, getting the dark would be 8, because there are 8 of those. But because you ate one of the crunches, there's actually 24 left, not 25. And then you eat that one, and you got 2. So now you're going to select another crunch. So this is the second crunch. Well, okay, so far you've eaten the crunch, which knocks that down to 5 instead of 6. And you've eaten 2 candy bars total, so you're now out of 23 instead out of 24. So you'd actually have to multiply all of these things together to finish this problem. So again, most likely calculator work is 4 times 6 times 8 times 5. That gives us 960. And on the bottom, 25 times 25 times 24 times 23. 345,000. So now what I'm doing is going to convert that. I'm just going to divide it out, and what I get is 0.00278, which is a big decimal, or actually a really small decimal. It's going to round it to 0.28. And that is really, move the decimal point 2 places, only about a 0.28% chance of that happening. Less than 1/3% chance. Be a very unique situation. So finally, 58 says, which parts of number 57 are independent and which are dependent, and explain why. Well, let's start with the first part right here. Anytime it's the first event, that's independent, because there wasn't anything to affect it beforehand anyway. Okay, I had said something about the crunch being like it would be even if the almond thing didn't happen. That's the very definition of what independent means. Independent essentially says that the probability of this doing this is not affected by what happens beforehand. The fact that we chose an almond and put it back in the bag has nothing to do with us choosing the crunch the second time. That's independent. Okay, but see, the third one says, okay, you've eaten that crunch bar. Now, normally, the probability of getting a dark would have been 8 out of 25. But because we ate the crunch bar, that makes it 8 out of 24. This probability depended on what happened before it. It depended on the fact that we ate that crunch bar. The easy explanation for the rest of this is that once you have one dependent probability in a series like this, everything after that is dependent. Because this probability is different than what it would have normally been, because we ate 2 crunch bars. We ate a crunch bar and we ate a dark bar. Either way, the idea is it's dependent based on prior events. They're definitely dependent there. Okay, we're down to the last type of probability that we're going to deal with, which is called mutually exclusive and inclusive probabilities. Number 59 was the mutually exclusive example. So it talks about having a fundraiser, and it says you sell 100 raffle tickets. 2 tickets win free Penguins tickets. 4 win a puck, and 1 wins a Crosby jersey. What is the probability of getting a winning ticket? explain why these events are mutually exclusive. Let's start with the explanation part first. Explaining why is actually a really simple thing, but it's always good to do it in the context of the problem. Mutually exclusive means that essentially you only get one possibility for anything that you would do. For example, one ticket leads you to only one possible result. Like one ticket would give you a penguin ticket, but you can't get the same ticket to give you an autographed puck or an autographed Crosby jersey. So whatever ticket you have, if it's a winning ticket, it's still only going to win one thing. So there is nothing that crosses over. There is no ticket that would give you more than one outcome. That's mutually exclusive. So it comes down to probability then to calculate it. For the Penguins ticket, to get that it would be 2 out of 100. Right? 2 winning tickets out of 100 possible. To get the puck, it would be 4 winning tickets out of 100. And to get the Crosby jersey, just a 1 out of 100 chance. Mutually exclusive probability says if you want to know if all of these things are considered good outcomes, all you have to do is add those probabilities together. And you get the probability of getting a winning ticket, which would be 7 out of 100. Now it doesn't specify which ticket you would get. It just means if you want a winning ticket in general, in this case it would be 7 out of 100 chance. Number 60 is a bit more complicated. Number 60 says you have this hand of cards that you have the 7, 8, 9, and 10 of hearts. You can win by drawing one card that will give you either a straight or a flush. So if you don't know what a straight is a series of 5 cards in a row. So that means that we could either get a 6 that would make us 6, 7, 8, 9, 10. This is just so we know what we would need for 6. Or we could get a jack, which would make us 7, 8, 9, 10, and jack. So a 6 or a jack is a good card. And then a flush is having 5 cards of all the same suit. So we already have 7, 8, 9, 10 of hearts. Right? So we want one more heart to make us a winner. Well, that means any heart would be a good card. Okay, assuming all the cards that can make you a winner are still available, meaning they're all still possible to get them, and that there are 36 cards remaining, so we're only dealing with 36 cards, not a whole deck. What is the probability of getting a winning card? And then, which cards make this inclusive probability? So, let's talk about that part for a minute at the bottom. Which cards make this inclusive probability? Inclusive means, is there an outcome that would fit more than one of the categories you're looking for? It sounds funny to say it, but is there a card that would be a 6 and a heart? Well, yes, the 6 of hearts. And the same thing goes for the jack of hearts also. So what it means is it's inclusive because there are cards that actually count as both things. For example, if I left off the heart part and I said, if I want a 6 or a jack, is that inclusive? Well, the answer would be no, because there are no 6s that are also jacks. So the idea is that because there's crossover between all the hearts and all the 6s and all the jacks like that, we have to think of this as inclusive, not mutually exclusive. So let's finish this by figuring out the probability here. There are 4 6s in a deck of cards, and it says they're all still available. So 4 6s out of 36 possible cards. Okay. There are also 4 jacks out of 36 possible cards. And then the hearts. Well, you already have 4 hearts in your hand. So normally there are 13 in a deck of cards, but since you already have 4 of them, that must mean there's 9 left over, so 9 out of 36. These are probabilities you would add together because they would all be considered good outcomes, just like in number 59. But we also have to consider the probability of the 6 and jack of hearts. there are two of them, right? The 6 and the jack. We counted them twice because we said, okay, I got all the 6s accounted for here, and I got all the jacks accounted for here. Then I turn around and say I got all the hearts here. Well, the 6 and jack of hearts are part of this, so we have to remember that we can't count stuff twice. So I'm going to subtract off the probability of getting the 6 or jack of hearts, which is 2 out of 36. So when it's all done, I've got 8 and 9 is 17, minus 2, 15 out of 36. And if you reduce them by 3, you get 5 out of 12. And that's the last of the probability review. And we're about ready for the midterm.